And welcome to everybody to webinar 4. Thanks for coming out tonight and seeing what we're going to do about the wave symmetry choices. Let's move right along here. Let's see if we can get this going. There we go. In the introduction, I am a consultant for both wave and Oculus. Private solo practice, contact lens only, and primarily focused on irregular corneas is really the focus of my practice and has been for the past 30 years. I previously had done national clinical support for WAVE on a case-by-case basis, and I've also presented, obviously, lectures and webinars for WAVE users. In addition, I also do private practitioner consultation services, and that's through a few different avenues, which I will hit at the end of the webinar tonight. I do beta testing for the CSP, the WAVE, and the AXL WAVE, which I'm currently working with now. And I did author the first WAVE certified designers program, and I'm currently guiding the WAVE training so that you guys can be more efficient in designing up your lenses. Tonight we're at WAVE, the fourth one down, WAVE applying R-Sym, G-Sym, and freeform. And we have a lot to get through tonight, so I might be going a little bit faster than I had in the previous webinars. So let's go back and recap. This was a brief review of webinar 3. We were talking about designing up a WAVE corneal lens, and we talked about these particular topics. First, we have to start by analyzing the anterior corneal surface. We then will take note of which areas we have extrapolated data, because obviously that's made up data and it's not really measured data, and that can influence some of our decision-making process when we're designing up the lens. Going through constructing the posterior lens surface, then constructing up the anterior lens surface, and then calculating out any residual cylinder that might be present as a result of us putting a rigid lens on that particular cornea. We also talked about understanding the difference between display differences but actual lens differences, and that is very important. So in the last webinar, we really hit the first topic there of analyzing the corneal surface, and then we also did cover the extrapolation areas and which things we need to pay attention to. So now we're going to get on to constructing the posterior lens surface. So when we're doing that, first we have to get an introduction into R-Sym, G-Sym, and freeform and what they actually are. And I did do a little bit of this last time, so these pictures would look familiar. But the posterior lens surface is all about the back curvature maps that are being displayed in WAVE. So when we take a look at the back curvature maps, these are R-Sym maps and R-Sym lenses, and we're seeing a map displayed on the WAVE screen. I've taken this out of the WAVE screen so we can concentrate on just these particular pictures. And the upper picture there happens to be an ortho K lens that's in R-Sym, and the bottom lens is a front toric multifocal that's in R-Sym. Next we have the G-Sym designs, and the upper one is the G-Sym ortho K design, and then the bottom one there is a back toric multifocal for, obviously daytime wear. And then we have the freeform designs. This happened to have been on a post PKI, and then on the bottom, that's a single vision lens that I had designed up. The bottom 3 images are 3 cases that we're going to go through today. So keep those particular pictures in mind. But understand, R-Sym, G-Sym, and freeform are about fit. It has nothing to do with optics. So when you're thinking about which symmetry do I need to employ for a specific case, it has nothing to do about vision. It's purely a fit consideration. And furthermore, idealizing the fit and idealizing the vision should really be thought of as independent variables. And actually sometimes, and specifically for irregular corneas, they can be mutually exclusive. So sometimes you may want to idealize the fit and compromise, and you have to compromise the vision in order to idealize the fit, and vice versa. Sometimes you want to idealize the vision, and you will have to sacrifice certain criteria about the fit. So sometimes you just cannot get an idealized fit and visual performance lens in the same design. And sometimes you have to come up with a compromise between the two. Okay, so this is the first case we're going to work on, and obviously we start with analyzing the corneal surface, but let's go back to the history first. 64-year-old, history of 40 plus years of hard lens wear and GP wear. This particular woman happened to have been unhappy about her mid-range and near vision, but was reasonably satisfied with her distance vision. Spectacle RX, I just chose the right eye to simplify things, so we're going to just cover the right eye here on this particular case. Was a simple RX, minus 150, minus 1 axis 120. And the current parameters on the right lens she came in wearing was a 712 base curve, minus 350 on the power. It was a 9.5 diameter lens with a 7.8 OZ. Those parameters are parameters that I measured off the lens. I measure every lens that comes into the office, so I know what people are wearing. The SIM Ks on the eye that were measured from topography were 4573 by 4712, and so you can see is about $1.50 a cylinder on the cornea there. And the lens was fit a little more than a diopter and a half steeper than the flat K. So here's the curvature map of this particular patient, and here's the best fit sphere of that particular eye. Now you can see it's not a very pretty looking eye, and I will tell you that when this woman came in, that cornea was actually considerably uglier than that. This particular topography was after I had already had a chance to design a lens to rehabilitate that cornea into this more improved shape. So let's move forward. Here's the best fit sphere, and just to take a look at an analysis of this corneal surface, we could see, I've put the cursor up there on the 7mm ring at 67 degrees, and we could see that we have a depression of 25 microns there. On the next one, I put that also on the 7mm ring, and we could see that we have an elevation of 6 microns at 327 degrees. So we really have, at a chord of 7mm, about a 31 micron difference between the high and the low point. Now, in general, when you're thinking about putting on a lens, and we're dealing with both elevated areas and depressed areas, 30 microns is kind of like a magic number to start thinking about, do I need a toric surface to on the back of the lens to stabilize it properly? So she's kind of right at that decision-making point there. However, she's a long-term previous wearer. She's got 40 plus years in, and she's also currently wearing a 9.5 lens, and a little more about that in just a moment. Also, movement has to be a little more excessive when you're taking a very established wearer versus a new wearer. Something I found out quite a number of years ago, that if you take a patient who's wearing a 9.5 lens, such as this particular woman was, which is moving pretty nicely all over that eye, and you reduce the movement by contouring the lens a little bit better to the eye, which you certainly can do with wave, what ends up happening is that the movement reduces, and you end up creating a whole host of problems that the patient didn't have before. So be very, very careful on long-term wearers not to reduce the amount of movement that particular eye is accustomed to. All right, so let's move forward. So here we have the measured HVID at 11.18. And over here, we could see we actually captured data out to about 9 millimeters of that. So we're missing about 2 millimeters of data out in the periphery. So here's the wave lens designs, or wave lens design that I came up with. On the left there is the horizontal, and on the right is the vertical. Now, I'm just showing you the two principal meridians here to keep things simple and move us right along. And we can see that the upper portion, we're displaying about 9.59 millimeters of the cornea on that line graph that's in the upper half of the wave screen. Remember last time we talked about that even if we have a selection diameter that's larger, we typically lose a little bit of the edge due to some internal workings of waves. So we're missing a little bit here because we have the diameter set at 9.8. And so we're missing about 0.21 millimeters of the very, very edge of the tip of the lens here on that upper display. Now, also, remember, she's wearing habitually a 9.5, and I typically would design up a much larger lens, given that the cornea was over 11, but because she's an established wearer, I do try to stay very, very close to what they came in wearing. Again, because if you go larger, not only does it create physiologic issues, it also creates mechanical issues where they can't get the lenses off because they're not accustomed to opening their eye up wide enough to get to the larger diameter lens. So we've got the horizontal and vertical displayed, and we see here that I've selected R-Sym on this design. And this is the very first lens that I did after the corneal rehabilitation, which was the new topography that I took, which was the one that I had just shown you. Okay, so we move along. We notice in the upper left of the quad display there, 87% of the cornea was covered by the scan, and it's in a rose color. And we remember that that means that when I brought the data in, that I averaged the astigmatism. Central astigmatism on the cornea is shown at 1.40 diopters at axis 178, and that's right there on the bottom right of the quad display. Yet the refractive astigmatism was -1 diopter at axis 120. So we really do have a mismatch of the corneal cylinder versus the refractive cylinder. Here, I put in 3/4 of a diopter of against the rule cylinder to create front surface cylinder on the wave lens because of the fact that we have that mismatch between the corneal surface cylinder and the actual refractive cylinder that she was manifesting. Because this front surface cylinder, I've put in prism to stabilize that front surface. And do remember that the back surface is rotationally symmetrical, so there's nothing that's locking this lens into place. So the only thing that's going to get this lens to orient properly rotationally is going to be the prism that's incorporated into the lens. We notice here that the average K is at 7.27 millimeters. Again, that's displayed in the lower left of the quad display on the wave screen. And I had chosen a base curve for this lens at 7.26, so it's basically an on-K fit. Let's move forward. I have it displayed in axial mode. There's a free-form display because I do want to get the most accurate representation of which areas of the lens are not perfectly in alignment with the front surface of the cornea. And I have it on the 70 micron display, which is the greatest resolution that we can see close to the corneal surface. Now, because we've incorporated prism, we can actually see that on that upper left graphic in the quad display, which is the interior surface, and you could see that white arc that's in the lower half of that lens. And that actually is the prism that's incorporated into this lens. Now, prism, when it's incorporated, thickens up the lens. And down on the bottom, we see that we have a lens-cornea relationship. Now, some people think that that's actually just a pretty graphic showing a lens on an eye, but it actually is not. What it is that the gray that turns into white, lower arc that we see on that screen is actually created directly from the topography data that's been fed into WAVE. So that is an accurate representation or a template of what the patient's eye really looks like. The blue arc that's on that surface that's just above that is the lens that you're designing. And again, that's not just a pretty graphic. What that really is a graphic that's being created directly from the manufacturing file, that ZWT file that WAVE generates that sends it to the lathe. And so that actually is an incredibly accurate cross-section of the lens you're designing. And you can see I've circled in red on the inferior portion there. You could see the increased thickness as you approach the edge, especially compared to the superior edge on the upper portion of this particular lens, and how much thicker that is down inferiorly. On the horizontal, we're seeing the nasal and temporal, and you can see that's kind of midway between where the superior and inferior thicknesses lie. And that should make even intuitive sense. Okay, so let's move on. We have here the 20 micron horizontal reference line that we spoke of before. And what you can see is that my black line that's representing the wave lens is all underneath the 20 micron horizontal reference line. And so I do know that the lens and the relationship to that anterior corneal surface does not really exceed 20 microns really anywhere. And do remember that when we evaluate fluorescein patterns at the slit lamp, we really can't see less than a 20 micron tear layer that has fluorescein in it because it just doesn't illuminate. So this, if I just put this entire lens on the eye just the way it is, and it's all under that 20 micron line, you would basically have virtually no fluorescein showing behind that particular lens. And so we take a look at the fluorescein pattern that wave is displaying. You can see it's for the most part black. There really isn't any fluorescein glowing. It's just a tiny little bit of it down on the inferior portion, and you can see that that's really where it just crosses above the 20 micron line. We actually have an edge clearance of about 35 microns. So you can see down in the lower portion of the sodium fluorescein graphic in the upper right of the quad display, just that little bit of tinge of fluorescein, and certainly that would be a very, very acceptable fit. All right, so let's move right along. Now, this is one of my really favorite final checks that I've done once I've done my lens design. What I want to do is I want to look at the gestalt of the lens. And the gestalt is kind of like, what's the overall feel of this lens? So what I'm doing is I'm comparing the lower left graphic, which is the back curvature graphic of the lens that you just designed, with the lower right graphic that's on the quad display, which is Wave's interpretation of what the cornea looks like. And for those who are using Scout, remember those curves are color matched. So in this particular case, this was a Scout topography. I would expect the colors to look fairly similar between those two and to also be distributed fairly similar. Now on the Pentacam, as well as some of the other topographies, there's going to be some nuanced differences with the original color scales that were displayed on the instruments, but Wave is still going to display this particular color graphic regardless of what the one looked like on the actual topography measurements and the scale that you happen to have displayed. So if we're doing a lens design, we still should have a reasonably close similarity, if we want an aligned lens, between the lower left graphic, which is the back curvature map of the lens, and the lower right graphic, which is the corneal interpretation that Wave is displaying for us out there in a color-matched curvature display. Okay. I've just blown that up a little bit here so we can see a little bit more detail about that quad display. So in the upper left, we have the anterior lens surface. In the upper right, we have that sodium fluorescein lens relationship. And then we have the posterior lens surfaces in the lower left, which is what we're talking about mostly tonight, about symmetry. And then in the lower right, we have Wave's corneal interpretation. And so the first thing is in the upper left, we can see, if you look very closely in the center, there's a yellow with a green tinge bow tie that's presenting in the center of this particular lens. And that's that green bow tie that's a little bit off the horizontal is sort of interlaced with the more vertical yellow bow tie, and that's representing the anterior cylinder that I put in at 3/4 of a diopter of against the rule cylinder. The white ring around that, that's the pupil, that's the patient's pupil, so we can see that's centered right in the visual axis of the particular patient. We also see the prism that's present there in that white arc that's in the lower portion of that anterior lens surface display. Then on the right, I take a look at the sodium fluorescein, and we can see, now that it's blown up a little bit, it's much easier to see that fluorescein down in the lower portion of that lens. And you can also see there's just a little bit that's displaying above the pupil almost straight up at the 90 degree, but it's very, very subtle. So for the most part, that's a very, very well-aligned lens. It's fairly homogeneous. And then on the back curvature, which is the lower left, we want to see, does it look similar to the corneal shape? And we can see that that lower left and the lower right one do look very, very similar to each other. They're not exact, but they're certainly very, very close. Now, what do I mean by proper shape? Well, for proper shape, you actually have to go to the back curvature screen, which is this one. So the back curvature screen gives us a line graph. That's that black line graph on the upper portion of the screen. And then when we take a look at that, the highest portion of that black line represents the steepest amount of curvature. So if we take a look in the graphic that's on the right, we could see the orange that's sort of all over the center, which is obviously representing the hottest curves or the steepest curves. And it also shows on the line graph as being the highest portion of that particular screen. And as we go out toward the periphery, you can see that the black line is coming down a little bit lower, and that's because the lens is flattening as we move from the apex out to the periphery. So that's the posterior lens surface on this particular lens. All right, let's go to case number 2. Very similar to what we just did. We're going to start with analyzing the corneal surface. So this is a 46-year-old. History of several soft lenses, and they all failed. We also had a history of several GP lenses, and those all failed as well. One reason or another, this patient had not been successful with any of the attempts. You can see the spectacle RX on the right eye is a -3, -5 1/4, axis 55. So it's oblique cylinder and quite a bit of it at that. And now he's also got a 175 add as a presbyopia has hit him as well. And the simulated Ks there, you can see there he's got about 5 diopters of cylinder right there on the cornea from the topography. So we take a look at the curvature map. And on the curvature map, it's a little splotchy looking, so we also have a little bit of a tear film, given that this was a placido disc-based topography capture. But if you look at the cylinder, it really is fairly well contained centrally. If we take a look at the best fit sphere, we have a much better idea of what's really going on in this cornea in terms of elevation. So let's take a little closer look at the curvature in the best fit sphere. And if you remember in the previous webinars, I've talked about curvature does not equal elevation, and this is such an important concept not to forget. If we take a look at the curvature map, I've gone ahead and put down a indicator at the chord of 7 millimeters. And we could see where the black ring is at the 7 millimeter zone, that for the most part, the corneal curvature looks fairly homogeneous. It's all basically blue. Down in the inferior temporal quadrant there, we got a little bit of green glowing over there, but for the most part, it really is blue, and it looks fairly homogeneous. If we do the same thing on the elevation or the best fit sphere, where we're understanding what the elevation is, we could see that it is not homogeneous at all. In the upper right and the lower left, it's kind of hot, very red, and in the upper left and the lower right, we could see it's very blue. So again, that concept of curvature does not equal elevation is an incredibly important concept to always keep in the forefront of your mind when you're taking a look at curvature maps, because you can very quickly forget about the fact that that really doesn't tell you about the shape of what's going on that particular cornea. So the elevation at the 7 millimeter chord along the 49 degree meridian there, as well as that depression that's going along the 7 millimeter chord at the 139. And so those are the two principal meridians on this, and it's obviously a very toric surface. So let's take a little closer look at that and see what we have here. So at 7 millimeter chord, you could see that we have, at the 49 where it's elevated, we have a plus 19 microns. So it's elevated only about 20 microns. Remember, that 20 micron line on the wave skin is not even all that high. If we take a look now at the 139, we have a depression of about 49 microns, so that is quite a bit more. If we then go over to the 229, we're at an elevation of plus 39 microns. And then if we come over here down to the 319 meridian, we can see we have a depression of 44 microns. So we go ahead and take a look at those numbers. We have the elevations at the along the 49 and the 229 meridian, and so we'll add those together, divide them by 2, and we have an elevation that's averaging at 29 microns on this cornea at 7 at a chord of 7 millimeters. And so the deviation of those two elevation points is only about 10 microns from my average. And so I think that's actually a very good representation of how high is the elevation of this cornea. It's about 29 microns. If we take a look at the depressed meridians, which is the 139 and the 319 meridian, we average the 49 and the 44 together, we have a 46 micron depression along that meridian, and there's only a deviation of 2 microns, so that's dead on in terms of really how depressed it is there. So we take a look at the 29 and the 46 that we came up with as the average elevation and depression. We really have an averaged toricity at 7 millimeters of 75 microns. Now remember, on the previous case, we talked about the 30 microns as where you have to start thinking about toric surfaces to deal, in terms of the lens, so that you have enough toricity on the cornea to deal with a lens that's actually going to line up properly, and you have to maybe start thinking about putting toricity into the back surface of that lens. Here, we're well in excess of that at 75 microns, and this is only at a chord of 7 millimeters, and if we're going to fit the lens larger than 7 millimeters, which, spoiler alert, we are going to do that, we actually have even more toricity than that. So this, we definitely would need a back toric surface to deal with this particular eye. Even though, when we looked at that curvature map, it didn't look all that dramatic, and it looked like the cylinder was really all centrally contained. So let's move on. Okay, so we take a look. We have a measured HVID at 11, a little more than 11.5 millimeters, and we captured data out to 9.5 millimeters on this particular eye. So we are missing a couple of millimeters of data on the outside portion of this. So here's the lens design that I did for this particular patient, and I've shown here along the flat meridian, which is the 45-25 meridian, that's being displayed in wave on the left, and then along the steep meridian, which is the 135-315 degree meridian on the right. The cornea lens that's being displayed in the upper portion, even though we have the 11.5 lens, is 11.29. So we're missing just a little bit of the display there. Now remember, we only captured data out to 9.5, so we are missing the outer 2 millimeters of data, which means that the relationship out there at the very edge between the lens and the anterior corneal surface is a little bit of a fantasy, because that's all extrapolated data, and you have to take that with a grain of salt because it's not real measured data. Okay, so let's move on and see what we did to do this lens design. So here we clicked on the G-Sym to create the geometric symmetry that we had talked about last time. I did not add any front cylinder to this lens to deal for optics. So in essence, we're creating an SPE, or a spherical power effect lens, to deal with all the cylinder that's on this particular eye. No prism needed. And in fact, because we have so much good toricity on the cornea, and we're going to create a G-Sym back surface lens, this lens is actually going to be rather stable because of how much toricity on the back of the lens is going to lock it into place with the toricity that's on that cornea. The average K is 749 millimeters, and you can see here I have a base curve. The median base curve is 748. You'll notice that there's another number after there, that's plus minus 0.24. I'm going to talk about that a little bit in the third case, not so much in this one. But it's basically a mid-K fit is what I designed for this particular gentleman. Okay, so let's move on. We see here we have 85% corneal coverage, which is wonderful. That means we did capture a lot of the cornea. And once again, it is a rose color, so you can see that I inputted the data into wave and averaged the stigmatism when I brought that data in. Central corneal cylinder, you can see it's just about 5 diopters at axis 49. And that really worked very well because we had the refractive astigmatism at 5 1/4 at axis 55. So just a couple of degrees difference between where the cornea was and where I refracted the gentleman. All right, so let's move on. Again, here's an axial display. We have a freeform display, again, so I can make certain that I'm seeing all of as close to the truth as I can about this particular cornea lens relationship. And again, it's in the 70 micron or the highest resolution display, so I can see the most of what's going on with the corneal relationship. Okay, once again, we have that 20 micron horizontal reference line, and once again, you can see my black line, for the most part, is all below the 20 micron line. So we look at the fluorescein display, and again, it's fairly homogeneous. It's pretty black. There's not a lot of fluorescein showing, except down really at that bottom, where we have that inferior temporal edge. It's showing the greatest amount of clearance, and you can see it's popping up there on the left wave lens there, out on the inferior temporal side there, and the clearance there is about 50 microns. Again, a very acceptable amount of clearance for the edge to create a nice peripheral pool for this particular design. Again, we're going to compare that gestalt of the wave lens back surface with what the cornea or wave's interpretation of the cornea looks like on the lower right of the quad display. So once again, I've blown that up for us so we can see that a little bit better. And again, the anterior lens surface, the sodium fluorescein cornea lens relationship screen, the posterior lens surface, and wave's interpretation of the cornea. And once again, on the interior lens surface, if we look centrally, we can see right along the 45-degree, that darker green bow tie that's forming. And then in the 135 meridian there, we can see the lighter green bow tie that's interlocked with the darker green going along the 45. So that's the cylinder. Once again, the white circle is the pupil, so we're kind of right there in the dead center of the visual axis. Again, looking at the fluorescein relationship, it's fairly homogeneous. In this one, we have a little bit more inferior edge clearance than we did on the last case, but I think that's perfectly fine. And once again, we want to take a look and make sure that the back curvature has that similar appearance to the cornea, which if we take a look at that, we can see kind of the reddish orange on the right kind of matches up with my cylinder bow tie on the left. We could see around that is the yellow on kind of both of those screens. Around that is the green, and you can see the green is kind of almost the same size in terms of dimension as what's going on the right. And then outside of that, we have the blue down to the black. So we do have a very, very good similar relationship between the lower left back curvature map that we've just generated for this lens design, and then the lower right, which is Wave's corneal interpretation. Now, as far as the shape goes, we once again take a look at that back curvature line graph. And again, the highest point is going to be the most curved. And of course, we have the most curved along the steepest meridian, which is why I've put the radar up at the 135 meridian there. And you could see that the highest point of that black line is really all through the center. And as we move out toward the periphery, it's coming down lower in the field, representing that the lens is getting flatter out in the periphery. All right, let's go to case 3 and analyze the corneal surface once again. Here we have a 40-year-old. History is post-LASIK, and he was a scleral lens failure. In fact, this patient was an out-of-towner that traveled in to see me and only actually gave me 5 days to get him successful. And all I remember about this particular gentleman is him sharing with me the absolute life-changing experience he had with his scleral lens causing him so much pain that the only criteria he gave to me to solve his problems was, I can do anything I want, but I am not putting a scleral lens on his eye because he will not accept it. So he came in telling me he will not take a scleral lens for this particular eye. His RX in spectacles was refracted at -250, -1 axis 180, but you can see the acuity is still horrible at 2400. And the simulated Ks are rather dramatic at less than 30 on the flat and about 43 on the steep. So that really is not a very pretty eye. You can certainly see that the eye has certainly suffered a significant amount of trauma from the LASIK surgery, and you can also understand why the -250, -1 axis 180 didn't really correct him better than 2400 vision. If we take a look at the best fit sphere, we get a better sense of the elevations on this particular eye, and you can see they do not look really like what's going on the curvature map. So let's take a look at this against the absolute scale display that we have over here. And here I measured up the extremes of curvature. And if you take a look at where I'm pointing in the upper right portion, it's what's that, at about 50 degrees or so, you could see that my cross is actually on an area that's not displaying any color. And I did capture it at 3.03 diopters. And the reason it's displaying is there's no color to represent it because it's less than 9 diopters of curvature. So the display just didn't have any color to actually represent the data that I actually caught on this particular scan. If we take a look at the steep, once again, you can see the same type of thing happened. I have a curvature of 127 diopters in that sort of blanked out teardrop shaped area, and once again there's just no color to represent it, so it was turning white, representing the 100 diopters of curvature. But then once I got into the steepest portion of that, there just weren't any colors to actually represent what was going on in this particular eye. So you can see the K values are certainly not the 44 by 4450 we see on the average corneas out there. They're 3 diopters by 127 in terms of flattest and steepest. So we have some very dramatic curves on this particular eye. So let's take a look. Here's the curvature. Here's that best fit sphere, so we can get a sense of the elevations and depressions on this eye. And here is a 3-dimensional representation of that. And that, I think, gives us a much better feeling for which areas are popping up versus which areas are really depressed down low. And do notice that when we take a look at the elevated area on the 3D surface, it's also a very flat area on the curvature map, but a very steep area on the best fit sphere, and indicating how I'm sorry, not steep, but a very elevated area on the best fit sphere. And so again, this really sort of accentuates that whole do not be misled by curvatures, pay attention to elevations, because here on the curvature map, say, oh, it's kind of flat in the upper right portion of this eye. Well, it is flat, but it's also incredibly elevated up there, and the elevation is really what's going to drive the fit, not the curvature. So let's move forward, and I've just put the 4 elevation maps over here so we can take a little bit better analysis of that. Here we see, and once again, you can see my cursor is actually in an area that has no color representing it because there wasn't any color to represent it, but we actually have an elevation of 215 microns along the 180, or I'm sorry, at the 0 on the right side. Straight up at 90, again, I'm kind of off the screen of colors, but I have a depression of 118 microns. Out on the nasal side, I am off the colors once again in the 180, and I have 172 microns of elevation. And then over in the inferior portion, that one actually is captured with colors, and you can see we have a depression of 74 microns down in the 270. So at the 7mm chord, here's the summation. So we averaged the 2 elevated areas, which were the horizontal at 0 and 180, and we have an average of about 191 microns of elevation, and only a deviation of 24 microns, which really isn't too bad considering how irregular this surface is. When we take a look on the depressed areas at 90 and 270, we have an average depression of about 96 microns, and once again, the deviation is only about 22 microns. So I think that's a very, very almost normalized toric surface that we're dealing with here. Even though I had to average both sides over there, the high and low points of those averagings are really very, very close to each other. And we have an average toricity of about 287 microns. So that's a very, very large difference between the steep and flat areas at 7mm. And again, it's only at 7mm, not further out. If we take a look at the obliques, here at 14, we have an elevation of 18 microns. At 135, we have a depression of 19 microns, but at 225, we have a depression of 63 microns. You might have been expecting an elevation, kind of like we did on the 180-90 meridians, but here we actually have a depression there. And then into 315, we have an elevation. So what we can see here is that we don't have regular toricity or cylinder on these oblique meridians. So this does not obey the typical toricity rules that we would expect. And so here's the summary of the elevations and depressions on this particular eye. And you could see here that we really have deviated away from a normal toric surface, and hence the reason why we're going to have to design a much more complex lens to deal with this particular eye. So the measured HVID is 1179, but I was only able to capture about 7.5 millimeters of actual data. And so we're missing over 4 millimeters of peripheral data, which means that if we're going to design up a larger lens, we have a lot of made-up data that's going to be incorporated into this lens, and we're going to have to troubleshoot a little bit more from the slit lamp. Okay, here's the two lens design. I'm sorry, the lens design in the 0180 meridian and the 45-225 meridian. And in this particular case, I am putting up all 8 semi-meridians so we can get a sense of what this lens looks like all the way around the clock. Okay, the cornea displayed is at 11.28, but and our lens diameter is 11.5, but remember, we've only have real data out to 7.5 millimeters. So a lot of the periphery of this lens really is made up data, and so we really have to take all of the periphery that we're designing into this lens and its relationship with the cornea with a grain of salt. And we know even once we get the lens on this particular eye, we're going to have to do some troubleshooting about that, what's going on there. Okay, here's the, on the left is the 9270 vertical meridian, and on the right is the 135-315 meridian, so the other oblique. Again, the lens diameter is 1150, and we've only captured 7.5 millimeters. So let's go back and take a look at the horizontal and verticals of this particular eye. I did select freeform so that I can deal with the asymmetry of this particular cornea, and I did not put any front surface cylinder to this, so we're going to do a spherical power effect, kind of like we did on case number 2. Since there's none of that, and quite honestly, with the cornea being this irregular and with those big numbers of elevations and depressions, there's definitely no prism needed. This lens is going to be incredibly stable. Once it finds its exact position, it's going to lock into place and be very, very rock solid stable. Now, the average K is 841, but my median base curve is 877. So you might be thinking, oh, did he fit this flatter than K? Well, not really. And how did that end up happening? Well, if we take a look at the 0180 and at that 877, we notice that that plus minus number is at 301. So what does that mean? What it means is that when WAVE summarizes that particular number for base curve, the first number, the 877, is the median base curve, and then the plus or minus 3.01 are 2 standard deviation units of what curvatures are being created over the rest of the dimensions of this lens. So what that means is that 95% of the curves that are contained on the back surface of this lens are going to fall between a radius of 576 and 1178 millimeters of curvature. In dioptric values, that's a little more than a 58 diopter and a half curvature for the steepest areas, and a 28.67 for the flattest areas. So you could see we have a very, very large range of curvatures that are being represented by this particular lens, but that particular notation of the 877 plus or minus 3.01 does not really tell you where those curves are. And so because we don't know where the actual distribution of those curves are, we really have to look at this back curvature map to understand which areas are steep, which areas are flat. So going back to the display, both the horizontal and the vertical, you can see I only got 78% corneal curvature here. and that was captured by the topographer. And so we're missing almost 25% of the corneal curvature that we're trying to design a lens for. So that's a lot of extrapolated data. Once again, the peripheral astigmatism was average because you can see it's a rose color. The central corneal astigmatism, WAVE tells us it's over 12.5 diopters at axis 165. Yet the refractive astigmatism was 1 diopter at 180. So clearly there's a big mismatch there, but I think we can understand why that is. It has to do with the interpretation of all of that irregularity. Okay, so it is again an axial display. It's a freeform display, and we have 70 microns display. So again, I can see the greatest detail near the corneal surface. Once again, though, you see at my 20 micron horizontal reference line, my black line is really not going above that at all. So when we take a look at the sodium fluorescein, we have a very homogeneous looking lens corneal relationship there. And the inferior edge shows about the greatest amount of clearance of 100 microns, but it really is at the very, very edge of the lens. You actually have to look very, very close to be able to see that over there. Once again, comparing the gestalt to the back of the lens, we could see that on the lower left, I have that sort of G-shaped steepness area that matches up pretty nicely with the G shape that WAVE thinks the cornea looks like of steepness there. And the rest of it looks pretty similar as well. So we did a pretty decent job of matching up the back of this lens with the front of this cornea. When we take a look on the quad display, we could see it in a little bit greater detail. Again, the anterior lens surface, the fluorescein relationship, the posterior back surface curvatures, and the corneal interpretation in WAVE. Now, in this particular case, when we look at the anterior lens surface, we could see that the central portion is a patchwork of colors. And so the power distribution there is not regular cylinder. It really is very asymmetrical. When we take a look, again, it's all contained within that white ring where the pupil is. When we take a look at the fluorescein, you can see that it is fairly homogeneous with that little sort of bright green arc down at the bottom and a sort of a lesser green up at the top to indicate that we have a little bit of a peripheral pool. But the back curvature really does look very, very similar to the corneal shape. But when we take a look at this one, notice that the highest points on this particular lens design are not in the center. And that should make sense because we already know that we had some elevated areas there out in the periphery. And so we could see here along that horizontal that in the on the nasal side there, that actually has the highest elevation of this particular lens and the steepest amount of curvature. Now, this is a new screen that you hadn't seen before, and this is actually the lens power distribution screen. And the noteworthy thing here is you can see it looks like a 3-leaf clover. Not a whole lot of symmetry. It's a very asymmetric power distribution. When you take a look at this screen, the hot colors represent negative values and the cool colors represent positive values. So what I did there is I put the cursor down so we could take a look and see what the powers were along each of those semi-meridians. And we could see along the 0, 0, 0 semi-meridian, the power is 158. When we pop up to the 45 degree, we're at minus 17 diopters. When we go straight up, we're at minus 17 and a little bit higher. Up at the 135, we have a power now of only minus 7, a little less than 7. Over here on the 180, we're at the plus side of plus 4, 4.25. Here we're at plus 3.25. Down at the bottom, we're at minus almost 3. And here down in the lower right, we have plus 9.25. So we could see there that the powers are distributed from a plus 9.25 all the way up to a minus 17 and change. We have almost 28 diopter variance of powers that are being created on this lens, and you could see it's not in any normal toric distribution whatsoever. So that's a free-form design. Do we have any questions? Again, this webinar series is really intended to provide fundamental knowledge, so please ask the questions that you'd like to see possibly covered in the future webinars. Just submit them in the chat box. For my private consultation services that I do offer, I have 5 avenues of help, and that's primarily targeted at advanced learning. For non-FDA designs, when the complexity is really above and beyond the help desk, that's what I'm here for, to help out. And you can do case-by-case help. You can find out more information about this all in that website down in the lower right there, that web address. But the case-by-case help is really learn the cases as they present to you, or perhaps maybe you took on a case and the case didn't go so well and you need help bailing you out. I have phone help, and that's based on per time units. And typically what that does is it targets learning for very specific cases or very specific types of problems that are on a case that may be plaguing you, and you cannot figure out what to do to solve the case or troubleshoot the case with success. I do one-on-one personal time, and what that really is a full day or 2 days targeting very specific weaknesses that you have, as well as what goals you would like to achieve. For example, you might want to have a stellar ortho-K practice, and we can concentrate everything all on ortho-K. Design and supply are primarily for non-wave users, where I will design lenses and supply the lenses for them. And then the DVD set, which was from the winter weekend workshop I had done a couple of years ago, and it is an enormous amount of material going through all the theoretical concepts and clinical applications of wave, ortho-K, scleral lenses, irregular corneas, etc. And then there are the wave resources here directly from wave, and I'm going to leave this page up here so you can take a look at all of that. And with that, that concludes webinar 4, and I'm glad we were able to get through all that material. I know it was quite a bit, and I did go fairly quickly, so I'm looking forward to any questions you might have.
So the first question is, what were the outcomes of these cases? Did you have to remake any of these lenses?
I don't remember about remakes. What I can tell you is all 3 cases were successful. Even including that LASIK case with that bizarre design that I had done with the 26 diopters of variance or 28 diopters of variance of power, that I actually achieved 20/25 plus vision, and he was actually delighted with that corneal lens. So even out at the extremes, and that actually was even a case that a scleral lens failed on and failed miserably on, corneal lens actually came in and saved the day. The first case was a multifocal for that established wearer, and she was absolutely delighted with her mid-range and near vision. I may have had to tweak things just a little bit from the lens I ended up showing here in the webinar, but whatever tweaks I had to do, they were very minor.
That makes total sense. Just kind of walking us through your initial design process and then making changes later based on what you see in the slit lamp.
Exactly.
Perfect. I have a question kind of asking about your methodology and why not use freeform for all of the cases? What are kind of the benefits of using like R-Sym or G-Sym?
In general, the thought process should be the simplest design that gets the job done is the one you want to use. You do not want to add in unnecessary complexity. And there's a phrase that I absolutely love and live my life by, not just designing lenses by, there's elegance and simplicity. And so you really want to take the most simplest approach because, for example, let's say we took that first case where I designed that R-Sym lens that was very successful for that very established wearer, and we did a freeform design because it was a little bit screwy in terms of the distribution of curves over there. Typically what would have happened on something like that is you can end up with an oddball optics that don't really work quite right. You will end up with variable performance. You can end up with malpositioning. Just because you see a freeform lens on a screen that lines up beautifully with a cornea underneath does not mean that that's how it's going to line up on the eye. You have other forces, including the lid forces, that can really wreak havoc with your designs. And so if the thought process of, well, I'll just design a freeform for every cornea that I see, typically leads wave users astray, and then they don't understand why it was that they couldn't get the case successful. It just adds in an unnecessary amount of complexity to a case, and troubleshooting can sometimes be absolutely impossible from that standpoint. So simplest that gets the job done is where you want to go.
Perfect. That makes a ton of sense. And I feel like that might be a similar answer to our next question, which is, why did you choose to average the astigmatism in case 3? when
I'm sorry,
you had. Why did
repeat
you
that again?
choose to average the astigmatism data in case 3
Oh,
as opposed to just using the raw data?
you mean the peripheral astigmatism and why it was a
Correct.
rose color. Do remember that that data was all made up anyway. We didn't really capture any data there. So now you're going to go ahead and bring it in unaveraged. Well, that's just going to wreak even more havoc with your design. And so why? Why would you need to do an approach like that? Like I said, you really want to pay very close attention to how much data you're actually capturing and which areas are extrapolated, because that really needs to guide your decision-making process as you move forward into the designing of the lens. And if you don't have a lot of data out in the periphery, basically what you want to do is start with the simplest approach first and then see what's wrong with that first lens that you get on the eye so you can troubleshoot it from the slit lamp. If you start adding in very, very complex curves into the periphery, and now let's say it was a very free-form periphery, and you didn't average the astigmatism, and the lens was rotated, 3 degrees, 4 degrees off axis, you really don't know what's causing which problems at that point. So my general rule of thumb is the only people I do not average astigmatism for are ortho K cases. Every lens that's going to be worn for daytime services, where it's through normal open eye wearing, for the most part, I always will average the astigmatism there because you get a much easier handle to work with what's going on in terms of your design.
Perfect. Thank you for that explanation. That makes a lot of sense. And I think a lot of people find that very useful going forwards. The next 2 questions both have to do with the way that you measured the elevation differences and kind of the elevation toricity at the 7mm chord. The
Right?
first question is asking why a 7mm chord as opposed to, say, like a 9mm chord or an 8 or like a 5 even. And then the second question is, do you have any specific cutoffs that you use to distinguish between R-Sym, G-Sym, and freeform, or do you use your best judgment?
Well, I'll answer the second question first. It's absolutely a judgment call. And at this point, I do that purely from experience. But on the first case, remember, I did point out that the toricity was sort of right there at the cusp of 30 microns, where you need to start thinking about a toric lens. Now, had that been a brand new wearer, I probably would have designed a G-Sym on that. But because this was a very established wearer for many, many years, I went with an R-Sym on that lens to make certain that I was going to get enough movement of the lens on that particular cornea, because I've learned from experience, and I've been burned enough times with that you don't take an established wearer and put them into a very well contoured lens. No good ever comes of it whatsoever. Now, on the first question, what was that again, Carver, that you had asked about the first question?
It was a question as to why you choose 7mm as the place where you look at the
The cord
elevation as
diameter.
opposed to another diameter. Yes.
Right. You certainly can go out to 9 or 11. Bear in mind the 7mm cord I have sitting there on the display, a 7mm ring. So it's a very, very easy reference point, and you are already typically outside the OZ, so you start to get a sense of what's going on in the peripheral cornea. Now, does that mean I always stop there? And the answer is no. Very commonly, I will go out a little bit further because I am designing out the lens considerably larger, and I do want to know what's going on a little bit more peripheral. But for the purposes of demonstrating what's going on here, as well as my first initial assessment, is typically done around that 7mm cord, because it's just a very easy place to get the reference data from. Then you have to actually put your cursors down, and this was on a Scout, but you could do that on any of the topographers. They all will give you that information out there. But do remember that if you capture data, for example, on the Pentacam, and you see all those little black dots indicating extrapolated data at 9mm, well, don't go assessing what's going on out there, because it's made up data. You really want to make sure that you're assessing measured data, not the extrapolated data.
Perfect. Just a few more quick questions tonight.
Go ahead.
Here's a very straightforward one. How do you determine your lens diameter?
That is very straightforward, and it's very easy to answer too. New wearer, non-ortho K, typically around zero point 0.5 smaller than the horizontal diameter. So for visible iris diameter. So if you have an 11.7 eye, I'd probably be right around 11.2 or so. So that is very, very straightforward. If it's an established wearer, such as we had on that first case, that is not the case. The lens will absolutely be smaller, especially if they come in wearing a smaller lens. So a lot of times what I'll do for those people is, let's say we had an 11.7 cornea and they came in wearing a 9mm lens. Well, I'm not going to design an 11.2 lens because they're going to be very unhappy, as well as, like I said, you can start to see physiologic problems crop up from that as well. So if I was going to design a little bit on the larger side, for example, maybe I was doing a multifocal or something, I would probably split the difference. So they were wearing a 9.0. I might have designed on a virginal wearer 11.2. So I'd probably design up a 10.1 as a first lens design and see if they can tolerate the slightly larger diameter, both in terms of the mechanics of getting it off, as well as the cornea is happy with it, as well as the dynamics during the wear is going well. And you'd be amazed on some of those people, even going to 9.5, they'll complain, oh, it's too big. I can't get the lens off. So sometimes you do have to attenuate that down a little bit. One particular case I had, she came in wearing a rather small lens at 8.5, and over the years, I've slowly increased the diameter. My initial lens was around 9, but now she's wearing actually an 11.5, but it also took me about a decade to get her up that large, so that I was able to sneak on a little bit larger diameter each year because of the fact that it was helping me position the multifocal better on that particular eye. Now getting to ortho K cases, 0.2 or 0.3 smaller than the horizontal visible iris diameter. And that's for minus, not for plus cases. Plus cases, 11.0 is almost a very, very good default for virtually every hyperopic case I do.
Perfect. That was a lot of excellent information. And it's always important to remember that, each case is different and, requires listening to your patient's needs and, how they interact with their own lens.
Sure.
All right. I have 2 final questions for you. We'll get through them very quickly.
Go ahead.
The first is, at the very beginning, you mentioned, fit and vision can be mutually exclusive. For example, in that final case where you have a more complicated cornea. How do you prioritize between fit and optics?
That really is an artistic decision when I'm designing up a lens. There's a lot of things that I will weigh out. If the fit is too compromised for the vision, I will sometimes throw the vision under the bus because of the fact that I'm not going to get the lens to perform right in terms of a malpositioning and or comfort problems or whatever the case may be. So, for example, in that last case, vision was not the top priority. Now, again, let's take a look at that last case for a moment. Getting a corneal lens on him comfortable was absolute a priority, and even though the optics were absurd, like I said, a variance of 28 diopters sort of sprinkled over that lens in terms of powers, you already know that that lens is not going to perform like a spherical power effect easily. There's an awful lot going on with the optics on something like that. But the truth is that his best correction is 2400 with spectacles. Honestly, if I can get him even to 2030, he would have been delighted. The fact that I got him to 2025 plus in that lens, that was just a bonus. So weighing out the priorities of the case, I think, are really very important as to how you need to sort of guide whether or not you want to prioritize fit, prioritize vision, or maybe come up with a good compromise for both and sort of head right there in the middle. It's sort of like the same thing with oxygen permeability issues when you're picking materials. One of the things that I tend to do is I tend to be a real big proponent of using Boston ES, which is a fairly low DK lens on my keratoconic corneas. Now, you'd say, well, why don't you use something with more oxygen? Well, the problem is that the ES tends to be a fairly rigid material, And as a result, that tends to work a little bit better in neutralizing out some of the aberrant optics typically associated with keratoconic corneas. I've learned in the past when I use a little bit higher oxygen permeable material, they also tend to flex a little more, and I get more vision complaints. So again, here's a case where we're talking about balancing physiology in terms of the material versus the vision. So I think that's always a balancing act that you have to kind of weigh out on a case-by-case basis and decide, which things are going to be the most important for this case to be able to make the case successful. Whether it's to make the cornea and the eye itself happy physiologically, or making the patient happy visually, or making you happy when you're taking a look at that lens on the eye.
Absolutely. That was a fantastic answer and kind of insight into how you fit your patients and fit your lenses to kind of end up with the best result. I have one final question. I know it's getting late. Thank you everyone for sticking with us. Throughout all three cases, you were using the freeform view, I believe, and as it says in this.
That's correct.
Is there ever a situation in which you'd use the G-Sym view, or anything not the freeform view?
Yes, there is. It's a very complicated answer, so I will keep that very, very simple right now. The only time I use the G-Sym view is when I'm designing hyperopic ortho K lenses. That's about the simplest I can make that. For everyone else, I'm using a freeform display view.
Great. Thank you for that answer. And on behalf of WAVE, I want to thank each and every one of you for sticking with us, for submitting your questions, and just for being here with us tonight. I hope you all have enjoyed the presentation. We hope to have you all here next month for episode 5. Dr. Molly, do you have any final words?
No, thanks for coming out tonight and listening to the material. I hope you guys all found it very helpful and give you a little more insight as to guide your designs. Wish everyone a happy holiday season and a great new year. I look forward to seeing you all next year.